Now we have defined the probability measure, which is a triplets, a sigma, a set of possible outcomes L. Then you define a sigma algebra, and then you define a probability measure. So there are some nomenclatures, some naming that we have to learn. Is that first one is that the elements of L are called sample points. So or a possible outcome. The second thing is that the elements of your sigma algebra are called events. So some of the subsets of L, let's say A is inside sigma algebra. Obviously, A is a subset of L. We call it an event. A is an event. If A is not inside your sigma algebra, we don't consider it an event. And the pair of L and F is called sample space. So your sample space is L and F. A probability space is the triplets. So we have a probability space, and we have another definition, because if we have a set inside F such that probability of S is equal 1. So we know by definition is that probability of L is equal to 1. But if you could find another set S which has probability equal 1, and if S is smaller than L, then we could reduce the size of our complication of probability. So if S is a smallest set which has a probability of 1, we call it support of probability measure. In other words, if we could exclude the portion of L which does not carry any probability, then we will get the support. So in other words, the smallest subset of L which carries a weight or a measure of probability equal 1, we call it support of your probability measure. So some more nomenclatures. So these are the words that we use, and we want to be very, very precise about them. So this is why I remind you. So outcome is a result of an experiment which cannot be decomposed into other results. For instance, if you roll a dice, your outcome is either 1, 2, 3, 4, 5, 6. You cannot reduce it. So you say that my outcomes are set of outcomes are either this phase or this phase or this phase. Obviously, you can assign numbers to them, and then etc. up to 6. So each of these guys is considered as outcome. The whole thing is your L, and so on. So sample space is the set of all possible outcomes. If you put all the faces from a dice, you get your sample space. And your sample space, we call it discrete if the set is countable. For instance, if L is the set of numbers between 1 to 4, so you can count it. You say element number 1, element number 2, element number 3, element number 4, or the set of integer numbers. So the set of integer numbers, n, this is an abbreviation of this one, is 1, 2, 3, etc. So I can count it. Element number 1, 2, 3, 4, etc. So I can count, and any member of these n, if you fix it like a million or so on, once, sooner or later, I will reach it. So in that case, I call this set countable. Let us have one example. You throw a dice. Obviously, your outcomes are these faces. So you have 6 possible outcomes. And then your sample space is going to be equal to these, and then you could define your a set. So a set A includes like one of the members. I call these an elementary event. Okay, provided that this is in your sigma algebra. Another event of having an even outcome, so it's phase 2, phase 4, and phase 6. So the null event is the subset of L which is empty. Obviously, probability of empty event is 0. Probability of L is 1. And probability of, like, if your dice is fair, probability of each elementary event is 1/6. So if you give this definition with the other properties of probability measure, so you have a complete definition of a probability space. Because using these definitions, you can calculate like probability of A. You can calculate probability of A, and then you could say that because you could define this as A2, A4, A6, and then A is the union of them, so therefore probability of A is equal to probability of A2 plus probability of A4 plus probability of A6, and therefore is equal to 1/2. So probability of any other subset element of your sigma algebra is defined. Another definition that we need is to define a set. We define a set as a countable set. So we say that a set is countable if we could have a bijective function, if there exists at least one, between A and the set of natural numbers. In other words, if I could get the elements of A for each element of A, I could get an integer tag at least, okay? So for instance, suppose that you have the set of non-negative numbers including 0, 1. So Z, the set of includes 0, 1, 2, 3, etc. up to infinity. I say that this is countable. Why? Because I could put a tag from this set. So this is my first element, my second element, third element, and so on. I could count them. So I put these bijective functions, which is I assign 1 to this one, 2 to this one, and so on. So I say this is countable. So countable sets and so on are important because they allow us, this understanding allows us to define discrete type random variables, discrete type probability spaces, and so on. So this is why I'm doing that. So in this example, I want to show that the set of rational numbers, so the set of, let's say, which is denoted by Q, which is the set of M divided by N, such that M and N are natural numbers. I want to prove that you can count the members of the set. So you could put a tag on elements of these, and then sooner or later, any rational number, you will reach them and give them a label, a ticket. And these tickets, they have one integer number on it. Because this is a bit complex to prove it, I will prove something simpler, and then I will show that the simpler problem is enough to prove this one. So what I prove is that I prove that the product of integer numbers by integer numbers is countable. So the elements of the Cartesian product of integer numbers by integer numbers are tuples. So you have two elements in each, so M and N. So I could put this set on a table. So I put numerator here, denominator here. Numerator is an integer number N, denominator is M. So let's say 1, 1, this element means 1 divided by 1. And then you have 2, 1, 3, 1, 4, 1, etc. And then here I put 1, 2, that means that 1 divided by 2. 2 by 2 means 1. So you see that for the set of rational numbers, these element and these element in here are not two different numbers, but in the Cartesian product, these two are different. So this bigger set, I could count it. How can I count it? I could count it as zigzag form. So I say this is my first element, second, third, fourth, fifth, sixth, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, etc. So you go zigzag, I'm sorry. So here, So here you have to go here. There is another element here, and then you go there, and then you go there, and then. So these zigzags is bringing. So you could count this one, but because from here you could have a set using that. So rational numbers are countable. So now we know the definition of a countable set. We know what is a probability space. So we could define different categories for probability space. If L, if the set of possible outcomes is finite. Finite means that it has 6 members or it has n members. So if L in general form has like n member, I could count it and I will end my counting at n. In that case, I call my probability space as a finite sample space. The second category is that L is countable, but it is not finite. Like it has the possible outcomes is x1, x2, x3, etc. So like you need to repeat some experiment till you are successful. Okay, and then how many times you repeat, we don't know. You may repeat only once, or you may need to repeat something millions of times. So if this is not necessarily finite but countable, so if L is countable, remember that this case is a subset of this case, then we call it a sample space. We call our sample space as discrete sample space. So remember that a finite sample space is also a discrete sample space, but a discrete sample space is not necessarily always finite. Okay, it's just discrete sample space. For instance, if your possible outcomes is like 1, 0, 1, 2, etc., like for instance, sometimes you need to transmit one packet to relay one information from one source to one destination. Sometimes your packet doesn't reach your destination, so your computer transmit it again, etc., till you have success. Some students they pass a course on the first attempt. Some they have to repeat it, take it again, till they are successful, provided that they don't give it up. So it is number of times that somebody takes a course, it produces a countable set, therefore the probability is a discrete sample space. So categorizing the sample spaces into discrete and continuous, we haven't learned the continuous type, is important because it helps you to simplify the problems. It is much simpler to work with discrete type probability spaces because it's intuitive rather than the continuous type. We'll learn about this very shortly. If the set of your possible outcomes is the set of real numbers, or a 2D plane, or a 3D plane, or a multidimensional k-dimensional space of real numbers, in that case, our sigma algebra is going to be a Borel field, and we call our sample space for Borel field, we call it continuous sample space. Okay. One example is that, let's say, the time that you will receive your first phone call after this lecture, or the time that you will get your first baby, if you ever get it, is a continuous sample space. If L is finite or countable, then sigma algebra is always is smaller than or equal to 2 to the power of L. Remember that if 2 to the power of L is the power set. Power set is the set or collection of all subset of L. And the number of elements inside the power set. So this notation means the cardinal number or the number of elements in any set. So if I say A, this means the number of elements in A. So the number of elements in 2 to the power of L, or the power set of L, is 2 to the power of L. This is an exercise, you can prove it. Sometimes we choose F to be the smallest sigma algebra containing a sequence of subset of L. This is called a Borel field. So we try to work with the smallest sigma algebra which could resolve our problems. So Borel field is what we need. So particularly, we need these for continuous sample spaces.